Have you ever wondered what would happen if you could travel back in time and prevent your grandfather from meeting your grandmother? This thought experiment is known as the grandfather paradox, a classic conundrum in time travel that presents a logical inconsistency. If you prevent your grandparents from meeting, you would never be born. Yet if you were never born, you couldn't go back to stop them from meeting. Quite a pickle, isn't it? This paradox has puzzled scientists and philosophers for years, creating a roadblock in our understanding of time travel. But physicist Lorenzo Gavassino might just have found a way around this. His recent research suggests that the paradox could potentially be resolved by applying quantum statistical mechanics to the concept of entropy in a closed, time-like curve. So how did Gavassino solve this age-old paradox? Let's delve into the world of quantum mechanics and general relativity. To understand Gavassino's solution, we first need to grasp a basic understanding of quantum mechanics. Quantum mechanics, in its simplest terms, is the study of particles at the smallest scale imaginable. Think atoms and subatomic particles. It's a branch of physics that describes the bizarre and often counterintuitive world of the very tiny. Now, let's dive a little deeper. Quantum statistical mechanics is a specific branch of quantum mechanics. It's the study of the statistical behavior of a system of particles. It's like taking a magnifying glass to a bustling city where each citizen is a particle and understanding the patterns that emerge when they interact. Now, how does this tie into entropy? Well, entropy is a measure of the disorder or randomness in a system. Imagine you have a box of puzzle pieces. A completed puzzle has low entropy, it's ordered. But if you shake that box, the pieces get jumbled. That's high entropy, a state of disorder. In the realm of quantum mechanics, Gavassino suggests that the entropy of a time-traveling system could potentially be reversed. That's like taking our shaken box of puzzle pieces and having it spontaneously return to the completed puzzle. It's a radical idea that challenges our understanding of time and order. Now that we have a basic understanding of quantum mechanics, let's explore the concept of general relativity. General relativity, another key player in our story, is a theory about gravity. In the simplest of terms, it's Einstein's brilliant idea that gravity is not a force pulling objects together, but rather, it's the curvature of space and time around massive objects. Imagine a trampoline with a bowling ball in the middle. The weight of the ball distorts the fabric of the trampoline. This is similar to how a massive object, like a planet, warps the space and time around it. Now, let's introduce the concept of closed time-like curves. These are paths in the fabric of space and time that loop back on themselves. Picture an ant walking on the edge of a paper cup. The ant starts at a point, walks around the edge, and without changing direction, eventually returns to its starting point. That's a simple visualization of a closed time-like curve. In the realm of general relativity, these curves could theoretically allow for something extraordinary, time travel. That's right, if you could traverse one of these curves, you might be able to journey into your own past or future. Now, remember our friend quantum mechanics from earlier? It's at this intersection of quantum mechanics and general relativity where things get really interesting. Some quantum interpretations suggest that traveling along these curves could potentially reverse the entropy of a system, making past events mutable. With these two concepts in hand, we can now understand Gavassino's groundbreaking solution. So, how does Gavassino's research solve the grandfather paradox? Well, Lorenzo Gavassino, in his profound exploration of quantum statistical mechanics, has proposed a rather intriguing solution. He suggests that a time-traveling system's entropy, the measure of disorder or randomness, can actually be reversed in what's known as a closed time-like curve. In simpler terms, this means that the progression of time as we know it, marked by increasing entropy, could be turned back within a specific framework of time travel. This could potentially allow for events, such as preventing the death of a grandfather, to be reversible. Imagine, for example, being able to go back in time, change events, and still return to a future that recognizes those changes, yet remains fundamentally unaltered. This not only provides a potential solution to the grandfather paradox, but also challenges our traditional views on time travel, highlighting the need for further understanding of quantum mechanics and general relativity.